The electrons will be drawn to the protons by a force F. Find the value of F. Okay, so what we need to get on our calculator is we need to get the charge of an electron, which is number 23. So what did I say here was 4 protons and 2 electrons, isn't that right? Yeah, and the distance is 0.09 nanometers. So the force is K Q1 Q2 over R squared. So the K, if I remember, is like 8.99 times 10 to the 9, is that it? Let me double check it. Yeah, 8.99 times 10 to the 9. So 8.99 times 10 to the 9, and then 2 electrons. So actually, let me get back my charge of 1 electron. So 2 electrons, 1.6 times 10 to the minus 19, and then the 4 protons is the same, 1.6 times 10 to the minus 19, all over 0.09 times 10 to the minus 9 squared. Okay, so let's type that in. Right, so I got a small number, 171 nanonewtons. Did you get something similar? No? Yes? Huh? 30? 32?
No, I'm getting 12.
Oh. Okay. Next one. JJ? Problem? Yes, no? It's okay, right? I don't think I typed in anything wrong. No, I made a mistake. It's not that. I did type it in wrong. You can see on my calculator. It's not 171. It is 228 newtons. I mistyped my 2 and 4. Okay, 228 nanonewtons. That's what you got. Yeah. You forgot the square, was it? Yes? Just this thing here? This square you mean, is it? Yeah. Okay. Number 2. An electron is orbiting 2 protons. What is the velocity of the electron? Okay. So an electron is orbiting 2 protons. And the distance here is 10 to the minus 10. And there's a force here. So you know that F equals K Q1 Q2 over R squared. But because it's traveling in a circle, you also know that F equals mv squared over R from circular motion. So you can make them equal K Q1 Q2 over R squared equals mv squared over R. So we can cancel an R here and here. We can bring the m down, and then we can take a root. So we have V is the square root of K Q1 Q2 over M or. Cancel the or, yeah. Bring down the M, yeah. Okay, let's have a calculation here.
Stephen, MD
Yep.
square, MD square over R.
I think that's the formula for motion in a circle for the force. Yeah.
The eighth one, you cancelled M with.
Well, I
R.
brought it down. I just moved it down. I made this one, look. I made this equal to this.
Okay.
Yeah. Okay. 8.99 times 10 to the 9 times, then there's 2 electrons. Okay. And then the mass of an electron is number 3 on my calculator. And then it's times the radius, which is 10 to the power of minus 10. So I should get a pretty big number. It should be moving pretty fast, and it is. It is 2250924. Or that's, what's that, 2.25 times 10 to the 6 meters per second. Yeah? Matches or doesn't match? Huh?
We accept if I found the acceleration equals to v squared over r.
You found the acceleration? Uh-huh.
Then acceleration equals to v squared over r.
Yeah. That's probably more how you do it in the final exam, because in the final exam they don't give you the formula like this. They give you the formula instead like this. Okay, number 3? Yes? Okay, number 3. An electron is trapped around a proton. How much energy is required to free the electron? If it is 10 to the minus 10 from the proton. Okay. So you have your proton here. You have your electron here. The distance is 10 to the minus 10. And the formula for potential energy, it's a negative, what is it? Minus K Q over R. Is that it?
Or square. R square, I think.
Is there no square?
Yeah.
No, there isn't square.
I don't think so for potential energy.
But you said you should ignore the negative.
Yeah, I just write it in to remind me that my answer should be negative. You don't have to write it in there, but I need to make my answer negative anyway. Yeah. The Q. Yeah. Okay. So 8.99 times 10 to the power of 9 times Q. Which is that divided by 10 to the minus 10. Right, so what's that? 14.4 with a minus joules. Oh, but I asked for it in electron volts, so actually in electron volts that'll be minus 8.99 times 10 to the 19 eV. Yeah? Now actually, this particular problem is not on the exam, okay? So you don't need to worry about this type in the exam. This calculating potential energy for this problem is not on the exam, okay? Yeah, I think that's all there is. That's all. Yes, so that's how much energy you need to give it. In fact, this formula is not in the formula book. And remember last time I was saying that I felt like this is too big? So I do wonder if I should have both Q's in the formula. But anyway, it doesn't matter because it's not something on the exam. So it's not something to worry about. What you need to worry about for the exam are problems like this and problems like this with Coulomb's law. Okay, so for the last one, you have an electron fired at a proton, and we imagine that the proton is fixed. And then what's going to happen is the electron is going to get closer and closer to the proton, and then it can't get any closer, and then it starts to get pushed away from the proton. So this distance here is 1 nanometer, I think I said. Yeah. Okay, any ideas about what we could do here? Any ideas? What type of problem is this? So I'll give you a little clue. Here it's at rest. No?
UV.
Not UV. So here this has kinetic energy but no potential energy because it's very far away from the proton.
Momentum.
Not momentum, it's conservation of energy. So here it has kinetic energy and no potential, whereas here it has no kinetic because it's not moving and only potential. So they must be equal. So you have a half mv squared equals kq. And you know what? I think I want to see what happens if I put the two charges in the formula. Because I do need to check this. I'll Google it, yeah. The problem is this is not... See, I'm not even worried about it because it's not on the syllabus, it's not on the exam. So it's not something I want to worry about too much, because it's not something you would ever be asked. So I'm not really caring so much about this right now. I have other things to be caring about. So do we know the M? We do. It's the V that we want. So I can say V equals 2K Q1 Q2 over M with a square root. Right.
Just one Q.
It is just one Q. Well, I'll be... Sorry. No, there's two Qs there.
Oh, okay.
Good.
Yeah, two Q. I thought that was a small letter.
Yeah, it was a small letter, a small Q. Right. Divided by the mass of the electron. Okay. Okay. So, not as big as of a number as you might have guessed. 22.5 meters per second. Whoops. Did you get that?
Which one is the Coulomb mass equal to?
Which constant number? 3.
Any.
Yeah. Can I scroll down? Right, so KJ checked for us, and there is both Q's in the formula. So it just means my answer here, need to multiply it by E again. Yes. So I get a much more reasonable answer. So that should be 14.4 electron volts. Okay. Now, listen. You could correct your notes from last week when I gave you the formula for potential energy, but I wouldn't even worry about that because, like I said, it's not on the exam. It's not, and we just really should prioritize things which are on the exam. So you need both Q's there. If you want to make the changes, go ahead. But again, I'm saying not on the exam for sure. Okay, the only thing that's on the exam with potential energy is they want you to draw the electric field line and the equipotential. So if you remember from the diagrams, all you need to know for the exam is that if you're on these lines, it's the same potential energy. Now the reason I'm giving you the formula is because I want you to see why these lines have the same potential. Because if you're on this line, your distance from the center is the same. So everywhere here is the same potential because in the formula you only care about how far away you are from the center, the ore. So that's why this one, they're all the same, and this one here, they're all a different radius from the center, or 2. They all have the same potential because the formula would give the same answer because you're putting in the same radius. So this is why they're equipotential. That's all you need to know for the exam. But I didn't like just telling you these are the lines where they're the same potential. I wanted you to at least see the formula with the or in the denominator that shows that they're the same potential. And then also what I wanted you to see was what happens when I increase the or? What happens to this potential? It gets smaller. This is the other thing I wanted you to know, but that's all you need to know for the exam. So like for example, in my last question here, where's it gone? Oops. Yeah. Why was I able to say that the potential energy here was 0? Well, I could say it because from my formula, if this ore is really big, so if it's very far away, then the potential energy is practically 0. Okay, because it's too far away from the proton. It doesn't really feel the force until it gets closer. So the potential is nearly 0 at a large distance. Okay, let's have a look at the next topic now. So for the exam, the type of questions which I have seen in the exam before, I've seen number 2 at least twice in the exam as like a section A question, and I've seen number 1 at least once in the exam. In fact, it's a little bit too easy for the exam because it's just a direct use of one formula. There's not even a second formula you need to use here. This is more like what you get in the exam because you need to use 2 formulas. This one from Coulomb and this one from circular motion. So this is what they like to do in the exam. Okay,